Hopefully that works. Normal density is a continuous density in the sense it is for a continuous random variable. Unlike binomial, binomial is for a discrete random variable, normal is for continuous. But before we can talk about normal densities, we have to understand something very fundamental about continuous densities. Here is the question. This is from last time. If we sum all the probabilities in a discrete distribution, let's just say binomial, what would that value equal to?
1.
1. And it is so easy because we have discrete values and we can add discrete values. So what is true with a discrete distribution is not true with a continuous distribution or density in the sense of a sum, because we can't sum over infinite values just like we have a discrete distribution. So do we agree that that's discrete? That is a discrete distribution. Can I add all of those probabilities for any of those outcomes? Easy. So one third, one third, one third. What does continuous mean? Continuous simply means all values between 1 and 2, all values between 2 and 3. So how many values do we have between 1 and 2? Infinitely many. How many values would we have between 2 and 3? Infinitely many. Is it feasible for us to add all probabilities infinitely between 1 and 2? No. So the concept of a discrete sum doesn't apply with a continuous density, which is why I wrote in the sense of a sum. But there is something else. Get it? Something else. One thing. Okay. So Who's a calculus? Okay, who wants to tell me what that would be?
An integral.
An integral, but I'm not going to write an integral.
I feel
And specifically, it would correspond to
the limit as the amount of bars go to infinity.
true. When you find the integral, what do we find?
Area under the curve.
The area under the curve. So, it's technically limit of Riemann sums, but I don't want to confuse you guys. So, it is related to a Riemann sum. What does the Riemann sum give us in limit? It gives you the area under the curve. So, with continuous densities, probabilities correspond to area under the curve. And that is very key to interpret probabilities that you would find with continuous distributions. It is the area under the curve. So I'll show you some easy examples as to how we find the area and so forth. But when the curve gets complicated, we just can't find it without using advanced math. The simplest density on a continuous interval is a uniform density. It is the fundamental density, the continuous density that we use. But you may ask me, well, where does the concept of densities come from? Long time ago, we had you can tell me what this is. Very good. That is a histogram that is defined between 1 and 2. And how many classes does it have? It has 5 classes. And would you agree that those probabilities are very, very much the same, or the frequencies? Yes? We also did something. We used this to find a curve. So we had a histogram, then we had the midpoints, and we drew a line. So here I could just connect the dots. And what is that line called? Huh? Getting closer. Frequency blank. Polygon. So that would be the frequency polygon, but still it's not a proper function. So if you take that and approximate it mathematically, Do you see the connection between the two? Now that is a well-defined function. It is a horizontal line on the interval 1 to 2. This, on the other hand, is not a proper function. If it's not a proper function, then we can't have a formula. If you don't have a formula, then we can't use the machine. So we need something perfect, and that would be a function. That part you need advanced math to do. This is easy. Why do we call it uniform? Between 1 and 2, the probability of something happening is the same. Do you agree? Now, you do have to keep in mind that that value is not a probability. That is rather a probability density. Why? I'm saying if this were to be a probability, I'm saying no matter what value I pick between 1 and 2, they're all certain to happen, right? Then if you go back to a discrete distribution and you add all the probabilities, it probably is not going to add to 1. It definitely will not add to 1. So how do we find an error probability here? We could say probability x is less than 0.32. Good. Less than 0.32. What do you think the probability is? So the data is between 1 and 2. Everything that you observed is between 1 and 2. And I'd like to know what is the probability that an observation would be less than 0.32. 0. Nothing over here. 0.32 is over there. And according to the density, all observations occur between 1 and 2. Okay. Probability less than 1.55. So 1.5 is right over there. That's 1.55 hypothetically. What would that probability correspond to? That probability would correspond to the area under the curve between 1 and 1.55. Why do I stop at 1? Because I already know that there is no probability below 1. Or I could say less than 1.55. In this problem, they mean one and the same. So how do I find that area? Well, you tell me. How do I find that area?
You know the height is 1, and the base of the rectangle is 1.55 minus 1, which is 0.55 units wide. Use base times height, and the area is 0.55.
Did we follow what he said? That is a rectangle. The base of the rectangle has a length, 1.55 minus 1, which is 0.55. And a height of 1, well, height times length or width times length, oh, it's 0.55, sorry. So 1.55 minus 1, that length is actually 0.55. And that's over there is 1. Multiply the 2. The probability is 0.55. Good. Now do we see what I mean by area under the curve? Yes. Okay. So the density we had earlier is uniform, which is simply a horizontal line, which is y equals 1, easy function, basic function. Things just got a bit complicated, do you agree? Slightly different, but still this is a continuous function, yes? Do you believe that the area under this curve would become 1? Well, it has to be 1, I'm telling you. So what would that area be? 0.15, 0.5, 0.3. So if I add all those areas, I'll call it A1, A2, A3, A4. I know the area of the 4 sections must equal 1 for it to be a density, and I've told you it is a density. So the first area is 0.15, area of the rectangle. Second area of the rectangle is 0.5. Third is 0.3. Since I'm telling you that it is a density, what should A4 be? I can simply solve, right?
0.05.
So it would be 0.05. Yes? It is the same as the area between 4 and 5. Do we agree? Because between 4 and 5, I have the area A4, which we solved, and we got 0.05 because the area under the curve has to be 1. Let's find the area between 1 and 3, or the probability between 1 and 3. The probability between 1 and 3 is the area under the curve between 1 and 3. What would that equal to? That would equal to this area A1 plus that area A2. Yes? So A1 plus A2.
0.65.
Here comes the tricky part. What is the probability of x is equal to 2.2? You can give me the wrong answer. Probability that x is equal to 2.2.
0.1.
How much?
0.1.
0.1. How did you get that?
Multiply the area, or the height 0.5 times 5.2 from the base.
0.5 multiplied by 0.2.
Yeah.
And you got 0.01.
No,
Okay.
0.1.
0.5, 0.2. 10. Yeah, 0.1. Okay. Now, this is what Josie did. I guess I'll draw right here. So, which is good thinking. She went between 2 and 2.2 and took the height, which is 0.5, multiplied those two together. So the height is 0.5 and the length is 0.2, which is 10 over 100. You get 0.1. Something is amiss with this logic.
We're taking the range from 2 to 2.2.
So, would this area of probability be the same as that probability? This probability is wanting to know, well, what is the probability that x is exactly equal to 2.2? Josie did apply everything right, but what she gave me is the probability between 2 and 2.2. See the difference? Yes? So, what would that equal to? Think about it this way. What Josie did, she took a triangle a rectangle between 2 and 2.2. But I want to make this rectangle as thin as possible so that I could find the probability exactly at 2.2. What would that be? What is the area of a point?
0.
0. Now, if you did mathematical statistics at the graduate level, we wouldn't say this to be 0. We would use a bunch of theorems and limits and say it is very, very, very close to 0, but not 0. It would be an extremely small value. But this is 0 as we are looking for a probability for a single point, not a range. So here it is 0. With binomial or a discrete distribution from earlier, would probability x is equal to something be 0? Earlier we wrote a table, 1, 2, 3, and I wrote the probabilities as 1/3, 1/3, 1/3. What is the probability that x would be exactly equal to 2? You can look at the table from earlier. I had x to be 1, 2, 3, and I wrote the probability 1/3, 1/3, 1/3. My question is, what is the probability x would be exactly equal to 2? One third. So with discrete distributions, we can find exact probabilities. With continuous distributions or densities, we cannot find exact probabilities. They are always 0. So if you do a homework and you have a continuous density, and if someone says, well, what is the probability that x would be exactly equal to this? It's always 0. So what is the answer to the last one?
$0.25.
0.25. How did you get that, Bio?
Well, we have the area 1, which is 0.15, and the area which we found should be 0.1.
So now Josie did the work and she gave us the answer for that part, right? That's 0.1. It's no longer a mess. So 0.1, and that over there is 0.15 because that would correspond to A1. So 0.15 plus 0.1 is 0.25. All of these probabilities have a name except part C. Cumulative. If you recall, when we were doing discrete distributions, I said anytime we have a less than, greater than, less than or equal to, greater than or equal to probability, all of those are called cumulative probabilities. And that one right there is an exact probability. Good so far? Yes? So we started with something nice, which is right here, and easy. The function with uniform is simply y equals 1 in that case. If you did algebra, well, you should have done algebra, f of x is equal to 1, a constant function. Easy. Well, what type of function is that? Algebra again.
That's a piecewise function.
It is a piecewise defined function, so I'm going somewhere with this. So can I erase this? Yes? So if I have to write f of x here, it would be 0.15 for 1 less than or equal to x less than 2, 0.5 for 2 less than or equal to x less than 3. Probably put open dots, but that's okay. I'm putting sort of like a parabola because I don't want to call it a parabola and then integrate it and then the area doesn't become 0.05. I don't want to do all that. This is some function I just don't know. It looks like a parabola or a polynomial. So we'll just leave it at that. I can't define it properly just by looking at it. But what I can define is the area, and I'm able to do that because I know the area under the curve must be 1. See the difference between the two? So I don't know what the formula for this curve will be. All I can say is that the area between 4 and 5 is 0.25 because I told you that this is a density. With me so far? Okay. Why did I do all of these. So initially it was a line. Then I illustrated a piecewise density. There should be some open and closed dot, but we can ignore that. Here, it's not that important. That is our bell curve, right? And let's just say that value six. The mean is 6. What is sigma squared? Long time ago. Starts with B, ends with E. Variance. So that's the mean. I was able to give you a function right away here, correct? Y equals 1. I was able to do all of that because that was easy. I couldn't tell you that one because I don't know, I just drew a curve. I do know what this function would correspond to, but can you tell me that there is a formula behind this curve? There has to be, right? It is a continuous function. You don't have to know this, but I will tell you what that curve will be. That is the curve, or that is the formula behind this curve. Okay? Now, if you took calculus, integrating that is painful, definitely painful. So you've got to do a whole bunch of things to integrate this. Even then, you won't get a proper answer. You can only approximate. That aside, the point I'm trying to make is behind every density, there is a formula, right? And anytime we have a formula, what can we do? We can use a calculator. So pick up your calculator. Suppose I want to find the probability between 7 and 8. So the lower would be 7, the upper would be 8, the mean is 6, the variance is 1, which means the standard deviation is also 1. So you just have to do normal CDF. 7, 8, 6, 1. What do we get?
0.1359.
0.1359. So that's area is 0.1359. It is the same as saying the probability between 7 and 8 for the random variable x. Good. Not variable, a standard normal distribution. has zero mean with variance 1. So you can take any normal distribution and convert it to a standard normal. What do I mean by that? I guess we could use the same over here from earlier. The mean is 6, the variance is 1. So 7, 8, 9, 5, 4, 3. Does anyone remember the empirical rule? No? You know, we put probabilities between, if it is within 2 standard deviations, it is this much. Within 3 standard deviations, it is that much, and so forth. Do we remember? Okay, if not, that's fine. So you could take any normal and convert it to a standard normal. I'm using different letters, X and Z over there. That is our standard Z score, X minus mu divided by sigma. So, if this is the value of X, and the mean is also 6, what would the Z-score be? So, the mean mu, in our case, is 6. The observation right in the middle is 6. Standard deviation is 1. So, what would that number correspond to over there? 0. What would that number correspond to there? 1. 7 minus 6 divided by 1. How about 8? 2. You need to catch on to this pattern now. I made this very easy. 9. 3. How about that side? Negative 1. Negative 2. Negative 3. Okay. It's poorly drawn, but my bad. It's okay. Very poorly drawn. Now it's better. If you don't recall the empirical rule, within 2 standard deviations, one standard deviation, we would have 68% probability. Within 2 standard deviations, we would have 95% probability. Within 3 standard deviations, we would have 99.7% probability. that picture coming back to your mind? Tiny bit? No. Should be in your notes. So, I just mentioned that the probability between -1 and 1 is 68%. In other words, we have to find probability -1 less than z less than 1. And that naturally is a bell curve with mean 0, standard deviation 1. So pick up your calculator, go to normal CDF. What should lower be? The lower endpoint. -1. Upper endpoint.
1.
Mean is next. What's the mean here? 0. Standard deviation?
1.
1. And tell me what you get.
6827.
0.6827. 68%. Yes. Now, let's do the same, but let's do -2 to 2. 0.9545. 0.95. Yes. The same, -3 to 3.
0.9973.
0.997, which is 99.7%. Yes, this is great and all. Go back here. What do you think the probability is between 5 and 7? Without using the calculator. 0.68. Let's use the calculator now and see if we get 0.68. In this case, though, the lower is 5, the upper is 7, the mean is 6, and the standard deviation is 1. What do we get?
0.6827.
0.6827, pretty much the same, right? If you compute it between 4 and 8, you will get 0.9545. If you compute it between 3 and 9, you would get 0.9973. Yes? So what can we infer from this?
That it's a standard normal distribution.
So this is a standard normal. Why do we call it a standard normal? You can take any normal distribution and convert it to a standard normal distribution with mean 0 and standard deviation 1. As long as you apply this transformation, which is linear, so there is a one-to-one connection between the two. Why did I bring this up? When you do the homework, it might say, oh, use this table in the back of the textbook, or use the appendix to use the table and get a probability between two numbers. You don't have to, right? So this is raw data. Those are z-scores. So if you have the data at hand, and if you want to find the probability between 5 and 7, you can find it directly using that syntax. But the homework system might say, oh, convert it to a z-score, use the table and find the probabilities between the two values, right? You don't have to use the table, that's what I'm trying to say. You can just use the calculator. I will go over the table when I do a problem, but it is not necessary. Does that make sense? Okay. If you go to the appendix, table A2. Okay, so if you look at this picture, it only talks about a standard normal. It doesn't talk about anything else, right? Because if you change the mean and the standard deviation, you would get a different normal, which is why we have the standardization procedure in the sense, no matter what mean, no matter what standard deviation you have, if you apply this formula, you can use that table. Does that make sense? Okay. So if you look in the positive side, or negative side, it is giving you the area for some value of z below 0, right? With me. So let's take the first case, -1. So the area below -1, to find that, you just scroll down the table. All the way up to -1, and we have 0.1562, no, 0.1587. Yes? So that is the probability below -1. Then you have to find the probability below +1. One is right there. And the first column is 0.00, 2 decimals, 1.001. So we have 0.8413. The last one was 0.1587. 0.8413. And we want to find the probability between those two. How do we find the probability between? We know the probability below -1. We know the probability below 1. I need to find the probability between -1 and 1. So that's given. That's given.
So just subtract.
I need to find that bit.
Oh.
You're right.
Oh, just subtract it.
Subtract those two. Remember with binomial I said just like subtracting and wiping things out. So if you subtract those two, 0.8413 minus 0.1587, what do you get?
0.6826.
0.6826. We saw that earlier. It was right there. Yes? Now, the issue here is these two tables summarize only for mean 0, standard deviation 1. What if I wanted to find the probability between 5 and 7? You can't directly use this table. But what you should realize, well, 5 corresponds to a z-score of -1. 7 corresponds to a z-score of positive 1. So that probability is the same as that probability, correct? Now I can use the table. Does that make sense? So, if you don't have a calculator, you have to go through all that to find the probability. What I am suggesting is, even if the homework system or the exam, you don't have to use it in the exam period, but if the homework system asks you to use the table, make that connection between this and normal CDI. And not 100% of the time, whatever answer that you get using the calculator is going to be more accurate than what the table would give you. Do you follow? So, is there something wrong with using the table? Absolutely not. But I personally think it is kind of inefficient to use that, in modern times. Good? But it's good to know. Any questions? Who's planning to take 21, 22, or is someone here who's planning to take that? The next level of stats class. I just want to mention that normal distribution is not the only distribution. There is T. This is the T distribution I was talking about. Some of you might need this later on. And there are other distributions, but the interpretation is the same. Chi-squared, F, they're all continuous distributions. Good? Okay, that is a good place to stop.